In this video, I'm going to be talking about the probability multiplication rule. In a previous video, I talked about basic probability and the addition rule. You should go back and watch that video before watching this video. If not, you're probably going to be lost. But let's talk about the multiplication rule. The multiplication rule applies when we want to know the probability of one and another event occurring, either simultaneously or sequentially or whatever order you want to talk about. And it could be more than one and another event. It could be the probability of multiple events. 1 and 2 and 3 and 4 apply. Now you can also think of this as the and rule. One and another, that means multiplication. We're going to multiply the probabilities for the individual events. Let's go ahead and look at a problem here, or an example. What is the probability of drawing the Ace of Spades and the Ace of Hearts on sequential draws, no replacement? No replacement means after we make the first draw and pull a card out, we're not going to put that card back in the deck for the second draw. Yeah, this is one of those situations. Multiply the probabilities for the occurrence of each event. And this is the proper mathematical notation for what we're doing. The probability of x and y equals the probability of x multiplied by the probability of y. But again, don't get caught up in the mathematical notation. Just understand what's going on. Yeah, we want the probability of an Ace of Spades and the Ace of Hearts. First thing we need to do is calculate the probability of pulling the Ace of Spades on the first draw. And this could be reversed. The order could be reversed. Don't get caught up in that. It could be the Ace of Hearts first, and then the Ace of Spades. We just want them sequentially. But for the purpose of illustration, we're going with Ace of Spades first. Okay, the probability of an Ace of Spades is 1 out of 52, or 0.0192. Now we need the probability of drawing the Ace of Hearts. Remember, there's no replacement, so we're not drawing out of a deck of 52. We're drawing out of a deck of 51. The probability of pulling an Ace of Hearts out of a deck of 51 cards is 0.0196. Now we multiply these two probabilities together to determine the probability of drawing these two cards sequentially. 0.0192 times 0.0196 is 0.0004 or 0.04%. Put that into some real numbers that we can relate to a little bit better. We would expect this to occur 4 times out of 10,000 possible attempts, or 10,000 possible occurrences. 4 times out of 10,000 would we draw the Ace of Spades and the Ace of Hearts. And if we tried this 10,000 times, it's only going to happen 4 times. All right, let's look at another more safety-related example of using the multiplication rule to determine the probability of system failure. In this situation, we have COVID-19 vaccine stored in a freezer at the required temperature of -13 degrees Fahrenheit. Electrical energy to run the freezer is provided by the primary electrical grid and a backup generator, a failsafe. If the primary failure rate is 0.0019 and the backup failure rate is 0.01, what is the probability of losing power, allowing storage temperatures to increase above the required storage temperature? We can use the multiplication rule because we have one of those and situations. Both of these failures must occur before the system will fail. The primary and the backup must both fail for the system to fail. And here is the mathematical representation of the multiplication rule. The probability of x and y equals the probability of x multiplied by the probability of y. The probability values are given to us in the problem. The probability of primary failure is 0.0019. The probability of backup generator failure is 0.01. So all we need to do is multiply those together. 0.0019 times 0.01. That gives us 0.00019, or 0.0019%. Let me go ahead and bring my calculator up on screen so I can prove it to you. We have 0.0019 multiplied by 0.01 enters. I'm not just proving it to you, I'm also double checking my math, which is always a good practice to get into. So when we multiply these two together, sure enough, 0.000019. We multiply that by 100, that converts it to a percent. 0.0019. We translate these into real numbers. We would expect this type of failure to occur 19 times out of every 1 million possible occurrences, or one occurrence for every 52,631 possible occurrences. In the next example, one more example and then we'll be done with this video, but in the next example I'm going to contrast the addition rule and the multiplication rule. This will illustrate how redundant systems, or systems with built-in fail-safes, will result in a much lower probability of failure, which can translate into safety terms into a lower risk for the system. We have a twin-engine airplane, and it's designed so both engines must function for safe operation. What is the probability of a crash if one or the other engine fails? The probability of engine 1 failure is 0.005. The probability of engine 2 failure is 0.005. So identical engines, identical probability of failures. But this is not an and multiply situation. This is or. It's asking what is the probability of a crash if one or the other engine fails. This is an addition rule situation. And mathematically, again, here's the addition rule for probabilities. Let's go ahead and work this out. We've got probability of engine 1 failure, 0.005. Probability of engine 2 failure, 0.005. Remember, either one of these failures occurs, the plane's going to lose power and probably crash. Add those together, 1 out of 100 times we're going to have a crash. I don't want to be on that plane. But let's look at another situation. Twin engine plane is designed so it can fly on one engine. Both engines must fail for a crash. What is the probability of both engines failing? Probability of engine 1 failure is 0.005. Probability of engine 2 failure is 0.005. We have the same engines that we had in the previous example. But in this design, the plane can safely fly on one engine. Both engines must fail for the system to fail. Again, this example over here, the system would fail if either engine failed. Over here, both engines must fail for the system to fail. This is the multiplication rule applied here. To find out the probability of failure for this system, we multiply the probability of engine failure. 0.005 multiplied by 0.005, 25 times out of a million, 1 out of 40,000. Our system reliability, our system safety is much better with a fail-safe, redundant, parallel design. This is a good example of why, as safety managers, we should, whenever possible, identify a backup system or some type of fail-safe design that can reduce our risk. It can reduce our risk dramatically when we have that kind of design implemented. All right, well, that's all I've got on the multiplication rule. I thought this last example here, I wanted to show you both the multiplication rule and the addition rule side by side. The next video we're going to talk about, it's mostly going to be a problem that you'll see on certification exams. All right, I will see you in the next video.